Okay, some solved problems for chapter 24. Here we have a capacitor hooked up with a battery. We're asked for first what is the charge on each plate. And we know there's a relationship between the capacitance and the charge and the voltage. Pretty simple. We know what the capacitance and voltage is. We can simply say the charge is going to be the capacitance multiplied by the voltage. We know the capacitance is 10 times 10 to the minus 6 farads. And the voltage is going to be 12 volts, kind of keeping this 10 to the minus 6 in the back of my head here. And I'm going to say my charge is going to be 120 microcoulombs. For part B, we are leaving it connected up to the battery. We're doubling the separation distance, therefore we're changing the capacitance. Capacitance is going to be equal to the permeability of free space multiplied by the area divided by the distance of separation. So what we're doing is we're doubling the distance of separation. So this new capacitance is simply going to be 1/2 of the original capacitance, which means it's going to now be 5 microfarads. Now we say our new charge is going to be equal to our new capacitance multiplied by the voltage. So it's going to be 5 times 10 to the minus 6 farads multiplied by 12 volts. And we're going to come up with a grand total of 60 microcoulombs on each plate. Now for part C, it says, okay, you've left the distance of separation alone, now you're changing the radius of the plates. Well, same deal. Capacitance is going to be permeability of free space multiplied by the area of these two plates. It's going to be pi times radius squared divided by the distance of separation. What this says is my new capacitance is going to be equal to 4 times my initial capacitance. That 4 comes because I've doubled my radius. So I double my radius, I square that, and I get 4. And that tells me that my new capacitance is going to be 40 microfarads. Do the same thing. My new charge is going to be equal to, I'll put a double prime on that. It's going to be, that is my new capacitance multiplied by the voltage. So 40 microfarads multiplied by my 12 volts. And I'm going to come out with a grand total of 480 microcoulombs. A problem on breaking down a circuit and finding out what the charges and potential drops are going to be. I've made it a little bit harder here by saying I'm going to figure out what the charge is on these 5 and 8 capacitors. So essentially I'm solving for every voltage drop or every potential drop in every charge on every capacitor. So I have this complicated looking circuit. First thing I need to do is take this 5 and this 8 and break them down into some equivalent capacitor. For capacitors in parallel, we know that the equivalent capacitance is simply going to be equal to capacitor 1 plus capacitor 2. So 5 microfarads plus 8 microfarads, and we're going to get my equivalent capacitance to then be 13 microfarads. Now we're going to take this series of 3 capacitors, 1, 2, and 3, and we're going to break those down into a equivalent capacitance. In this case, we know that these guys are in series, and so we can write 1 over the equivalent capacitance is going to be equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, or 1 over 10 microfarads plus 1 over 13 microfarads plus 1 divided by 9 microfarads, kind of keeping those micros in my calculator. And I'm going to come up with my equivalent capacitance to be a grand total of 3.47 microfarads. I trust you to peck that into your calculator as well. Now the first thing we're solving for is what is the equivalent capacitance of the system between A and B. So we've done that. That's 3.47 microfarads. Then we're asked for how much charge is going to be on this guy. Well, charge is going to be equal to the capacitance multiplied by the voltage, and we're told that there's 50 volts across this, so it's going to be 3.47 times 10 to the minus 6 farads multiplied by 12 volts. and we're going to come out 174 microcoulombs is going to be the charge on this equivalent capacitor. Now this charge is going to be the same as each one of these three in series. Remember, in series the charge is going to be the same for every single capacitor as with the equivalent capacitor. So there's going to be 174 microcoulombs on that guy. There's going to be 174 microcoulombs on that guy. There's going to be 174 microcoulombs on that guy. So the answer to part C is there's going to be 174 on the 10 microfarad, and there's going to be 174 on the 9 microfarad. Now let's just take a quick look at the voltages for these various guys, see if it makes sense. I know that the voltage for the 10 microfarad capacitor is going to be equal to the charge divided by the capacitance of the 10 microfarad guy, so 174 microcoulombs divided by 10 microfarads is going to be 17.4 volts. The voltage of the 13 guy, that's going to be the charge, 174 microcoulombs divided by 13 microfarads, is going to give me 13.4 volts. And the voltage drop across the 9 microfarad capacitor is going to be the charge, 174 microcoulombs divided by the 9 microfarads, or 19.3 volts. Now we know that everything is perfect if all three of these voltages add up to 50 volts. So if we take a look at the sum of these voltages, they should add all up to be 50. In this case it's going to be 50.1 volts, so we're feeling like we did something right. Now we know what the voltage drop is across this 13 microfarad capacitor. It's going to be 13.4 volts. That's going to tell us that there's going to be 13.4 volts across this 5 microfarad capacitor. There's also going to be 13.4 volts across this 8 microfarad capacitor. So what we can now do is we can calculate the charge that's going to be on the 5 microfarad capacitor. That's going to be the capacitance multiplied by the voltage drop across that guy. So that's going to be 5 microfarads multiplied by my 13.4 volts, and I'm going to come up with 67 microcoulombs. The charge that's going to be on the 8 microcoulomb capacitor is going to be my 8 microcoulombs multiplied by my 13.4 volts, and I'm going to come up with 107.2 microcoulombs. And if we take a look at the sum of all these charges, we know charge can't be created or destroyed. The charge must add up to be roughly 174, and we come up with 174.2 microcoulombs, so we're feeling like we did something right. Remember, for the capacitors that are in parallel, the charge must add up and the voltage drop is going to be the same across them. And for capacitors that are in series, the charge is going to be the same across all of them, and the voltages must all add up to be the voltage drop across the equivalent. And lastly, let's take a look at a problem dealing with energy as well as getting more capacitor practice. So I've written down kind of what we already know in this problem right here. For part A, we're asked for the capacitance. Capacitance is going to be equal to the charge divided by the voltage. So I'm going to have my 0.018 times 10 to the minus 6 coulombs divided by my voltage, 200 volts. I'm going to get my capacitance to be equal to 9 times 10 to the negative 11th farads, or I could also write that as 90 picofarads if I so desired. So for part B, we're asked for the area of each plate. We know that there's a relationship between the capacitance and the permeability of free space. the area and the distance of separation. Now we know the capacitance and the distance of separation, so we can simply say that the area is going to be equal to the capacitance times the distance of separation, which we know, permeability of free space that we know. So this is going to be 9 times 10 to the negative 11th farads. Distance of separation 1.5 times 10 to the minus 3 meters. Permeability of free space 8.85 times 10 to the negative 12th with a whole bunch of weird funky units. And we're going to get my area of the plates to be 0.0152 square meters. For part C, we're told that dielectric breakdown for air is going to occur at some electric field strength. So we know what our electric field strength is going to be. It's going to be 3 times 10 to the 6 volts per meter, and we're asked what's the maximum voltage that this capacitor can essentially take. Well, we know that there's a relationship between the voltage, the electric field, and the distance of separation for a capacitor. Maximum voltage is going to occur at maximum electric field, so that's going to be 3 times 10 to the 6 volts per meter. I know what the distance of separation is. It's 1.5 times 10 to the minus 3 meters. You can see that the units are going to work out to be volts, and I'm going to come out with 4.5 times 10 to the third volts is going to be the maximum voltage I can put across this air capacitor for this given distance of separation. Lastly, for part D, we're asked to solve for what the energy is. You can write the energy any number of ways. I'll simply do 1/2 charge multiplied by voltage. I could also do Q squared over 2C or any of those other ones that we have. So it's going to be 1/2 multiplied by the charge, 0.0018 times 10 to the minus 6, and then 200 volts. And I'm going to come out with 1.8 times 10 to the minus 6 joules, or 1.8 microjoules, if you will.